Have more Peters around, and so today we have Peter Patel-Schneider from Bell Labs, who can tell us about the Semantic Web and knowledge.
Although, if you ever Google me, you realize there's only one Peter Patel-Schneider. And that's a universal constant at the beginning of time, as far as I know. I guess, yeah, there's no chance. I will have, unfortunately, I will have to use this. Rats. Oh well. Okay. All right, we'll try it this way, although I don't like holding mics. But anyway, so I'm here to tell you a fairy story? No, not exactly. Cautionary tale. Maybe cautionary tale is about right. That has to do with the work I've been doing for part of my efforts last longer than I actually care to think of. I think it's about 5.5 years now. Having to do with, I think I described it best this morning, sweetness and light and representation to the semantic web. And you should understand that this is a very personal and idiosyncratic view of what the semantic web is and how it should be and what role representation is supposed to play in it. And I'm going to try and tie together a bunch of different activities that I've done the last while and tell you why people who care about the semantic web should care. So recently, I've been doing a number of things. My background is in a branch of formal representation called description logics, and I've actually built reasoners or inference engines or whatever. And you can actually build pretty fast ones for fairly expressive logics. I've been involved with in a sort of an ad hoc group of people that are trying to build different reasoners that act the same. So you have interoperable reasoners for the same language. And I've also been involved in the semantic web. A number of things in the semantic web, starting with part of things having to do with the formalization of RDF, which mostly was lots of sniping from the sidelines. In other words, complaining when people got it wrong and trying to tell them how to do it right. I'm happy to say I won. I've been involved in the Daml plus oil language and the OWL web ontology language, which is now a W3C recommendation. I've been involved with an extension of that to rules, an extension of that to first order logic, which essentially are proposals of how you might extend the semantic web to add more expressive power. And I've been involved in this new Sparkle thing, mostly again sniping from the sidelines. So this talk tries to tie together some of these activities into a fairly provocative whole and present a vision oops, of a potential future for the semantic web. That future is not something I've had much chance to look at because I've been too involved in doing other things, but it is some ideas of how the semantic web might go. Okay. And I'm going to have to sort of abstract and give an overview of things. I've got pointers to various papers interspersed throughout this presentation, which you can actually look at if you care. Okay. So here's an underlying thesis. Formal symbolic representation of information has use. Why do I claim this? Well, in a word, databases. Databases are formal symbolic representations of information that I claim has had fairly decent use in the last, well, since the relational database systems came along anyway. Okay. Evidence against, and actually quite a bit of evidence against as well, mostly here, right? Google doesn't do this. Google does information retrieval, by and large. Information retrieval is not formal symbolic representation of information. Okay? Similarly, most modern machine learning methods don't really do a very good job of formal symbolic representation, I claim, in a certain sense. Okay. So this is actually a thesis that's involved, it's behind my formal work, actually ever since I started my graduate school career and I've tried to stay pure to it, shall we say. Okay. Thesis 2 is the semantic web. Not just the semantic web, but say the web in general is actually a good place to do formal symbolic representation. Why? Well, because that's what the semantic web is supposed to be for a certain sense. There we go. I knew I had a quote for that. This is from the Semantic Web from Scientific American. Semantic web is an extension of the current web in which information is given well-defined meaning. Okay. But let's not believe Tim Berners-Lee, not because he doesn't say good things, but we would like to validate them ourselves. Why would we like to work in the semantic web if we believe in formal representation? Well, because it's there. And to tell you the truth, a lot of the old formal representation methods were academic toy things that had very little connection to applications or the outside world. The semantic web certainly has that. The semantic web is big, lots of sources of information. The other interesting thing about the semantic web, or the web in general, is that it really has, it's a robot in a certain sense. But it's a really nice robot. You don't have to worry about vision and motion. The semantic web has effectors and sensors in the form of services. Services are much nicer to deal with if you don't care about vision and motion than vision and motion per se. You just care about representation. It's just nice to have a service that you can call and something will happen. You don't need to worry too much about it. Okay. So here's a question. What's wrong with the semantic web, and why? What would it take to make the semantic web a good place for formal symbolic representation? Because I claim that right now it's not a particularly good place for formal symbolic representation of the kinds that I want to do, which I'll get to in a minute. And I think I'd have to qualify that statement a little bit, because the semantic web is changing in ways that I think are changes in the right direction. Okay, so perhaps a slight digression. What is the semantic web? Well, here is one Tim Berners-Lee's slides from a talk. I think it was from one of the XML conferences about 2000, where he has this view of the semantic web, where you have RDF and ontology and rules and all sorts of things built on top of what we might describe as the regular web. Okay. All right. So the semantic web is built on top of the World Wide Web. It uses XML, and IRIs now instead of URIs. International is more universal than universal in the web parlance. But the semantic web is built on top of these underlying things. Oops. Yes. The semantic web has several languages for representing information, namely RDF and its extension RDF schema, and more recently OWL for representing ontologies. So these parts of the semantic web exist. These parts are sort of being worked on. More coming. This part here, this rule interchange format, is being worked on as I speak and you listen. Oops, yeah, that's the end of that talk. Okay. So the semantic web is, the vision, of course, is that there's a lot of what we'd call representation logics, all the way up to logic frameworks and somehow proof and trust on top, although I'm not quite sure what they're doing in this same stack. And part of it exists nowadays with some tools to implement pieces of it. Okay? And people are actually using it in a limited way. It's certainly astonishingly much smaller than the web in general, but it is out there and people actually use it for limited amounts of things. So let's take a closer look at some of these semantic web languages. So RDF is this underlying language of the semantic web. It's really a language for representing very simple information, and this is as distinguished from XML, where XML, you might say, represents data, i.e. something tied to a particular document that is sent from a transmitter to a receiver and doesn't have much use outside of those two parties. The RDF is designed to be a place where you represent information that anybody can use. Okay? And one might, if one was feeling charitable, call this information knowledge in some sense. Knowledge is a pretty loaded term. I try not to inject many loaded terms into my talks. So I will try and cut down on the number of times I use knowledge. Okay? RDF is transported as XML, however. Okay? And all of it is transmitted in what we may call these subject, property, object triples. And some of these properties have built-in meanings. Okay? And we'll actually see some examples of this to make this much more concrete in a minute. Okay? And it has a few other things. It has some sort of existential variables. It uses IRR references for names. It's this very, very simple language that one can use to send information, not to send information, but to publish information on the web. Okay? RDFS extends this with a little tiny ontology language. By the way, what's an ontology? An ontology is roughly a way of describing the categories of things that are in the world. Okay? Nothing more than that. I would prefer it to be a formal language. Some people use pre-theoretic notions to describe ontologies, but that's all that I'm talking about here. RDFS uses the same syntax as RDF, namely triples, but it gives some of the properties, like this subclass property, special meaning so that this property is the relationship between a specialization and a generalization. That's all that it is. Okay? And there's actually a formal account for that now. Okay. OWL, on the other, is a much more powerful extension of RDFS and can represent a lot more ontologies. It uses the same syntax as RDF, sort of. And a lot of this talk is going to be about why I put this little caveat in there, and that has to do with why, in my opinion, this account of building languages in the semantic web is broken. Okay? And more, as I said, more languages are coming. Okay. And there's, by the way, there's lots of other pieces of the semantic web that are not blessed by the W3C, like rule languages and all sorts of other things that some people use as part of the semantic web. I'm talking here about the semantic web that's really, shall we say, the core that W3C believes in. Okay. So we can see here, this idea of several languages that fit together in a particular way, okay? And this vision came from the mid-1990s or late 1990s, where the idea that you would extend the web with information, okay, and give it a well-defined meaning in these two languages, written in XML, with names, and here's where we get to the interesting part of this vision. Not only will we have several languages that use XML and IRIs, but everything in the semantic web will be transferred as what we'll call these subject property object triples. And these triples will be extracted from the XML, okay, in a particular way, which is called RDF XML, or maybe it's XML RDF. I always forget which way around it is, but anyway. And so when we send a bit of XML around, we will parse it and extract these triples, and these triples will carry the meaning that we're trying to transmit or publish. Okay. And so here are some triples. Okay. These are not how they're written in RDF XML. They're written in RDF XML in a very, very ugly syntax. I don't know anybody who likes the syntax. Anybody here like the syntax? Anybody here know what the syntax is? I have trouble with the syntax. I've had to use it much more than I could ever have imagined. But what counts for the syntax is extracting these triples. So we have this vision where we're transferring information around or publishing information, and the information is carried in these triples. And so what do these triples mean in a certain sense? You know, well, there's some object in the world, John. He stands in this relationship called loves to this other object in the world called Mary. This same object in the world stands in the age relationship to this other object, which is, well, good question, 25, okay? There is some object in this Mary object, who John loves, and this is essentially an existential variable, someone. We're not sure who that is, but there is someone that Mary loves, okay? Loves has a domain of person and a range of person, okay? This is more of RDFS. And John is a type of person, And person is a subclass of agent, generalized agent. Now I've used some of these. By the way, if you don't understand this syntax, these things here are shorthand notions for IRIs, which in XML you would call Q names, but they're not exactly XML Q names. Just think of them as shorthands for much longer IRIs that usually start http://something, and then a hash sign, and in this case it would say agent. That's all you really need to know about them. They're names, and they fit into this addressing scheme that's used in the World Wide Web. Okay. All right, so I've now told you everything that was known about RDF and RDFS in the mid-90s, right? In, what was that, 1 minute, 2 minutes? Okay. All right. On this slide, because that's it. That's essentially what RDF and RDFS were in the mid-1990s. Now, notice I didn't give you any formal account of their meaning, okay? So, what is the meaning of these pieces of RDF? Well, good question, because there wasn't any document that told you, okay? There was a data structure that they were supposed to evoke, but that didn't talk about meaning, okay? So, what's the meaning of John? I don't know. It's a piece of syntax, right? What's the meaning of 25? In particular, is it a string or an integer? I don't know, okay? It's something, okay? Of this thing here, I said it was an existential variable, but even that wasn't very well defined. Of this loves relationship, who knows, right? What's the meaning of this triple? Well, who knows, right? It was a data structure, and the meaning was essentially the meaning that you should have gotten from reading these non-formal documents, okay? Now, having been through a long, bitter, and drawn-out debate in the representation community of whether this is a good thing, let me tell you it's not a good thing. If you're going to write things down in computers, computers are dumb, so you should have a good idea of what the things are supposed to mean, at least formally. So the computers might do the wrong thing, but at least, I mean, from the outside, looking at them as sort of artifacts doing whatever they're supposed to do, that thing that they're doing might be completely incorrect in the world, but at least they're operating as they are supposed to, right? It's not like you feed it into the program does something, and you can't even tell whether it's doing the right thing or not, okay? And that's the situation here. We don't know how these things are supposed to be processed because we don't have a formal meaning for them. And so this was actually noticed around 1999 or thereabouts anyway. And there was an attempt to clean it up, okay, and give a formal model theoretic semantics. If you don't know what model theoretic semantics is, I can caricaturize it for you in one phrase. Model theoretic semantics is essentially formally stating what should be blindingly obvious to any fool. Well, any mathematical fool, but but essentially, and if it's not blindingly obvious, then there's something wrong, okay? I mean, you should be just essentially stating blindingly obvious truths in ways that are very, very formal that you can then prove what should be happening. And this was done in this W3C working group, a few years ago, mostly by Pat Hayes. And whenever he made a mistake, I would complain to him, and he would fix it. And when he made new mistakes, I would complain. And this went on for a couple of years or so. Now, admittedly, Pat was in this horrible situation because he was trying to write down the things that everybody else in the working group thought was blindingly obvious, but they had different ideas of what should have been blindingly obvious. And this, of course, is part of the problem. So he had to pick one, and he had to convince them to say, this is what it meant, or as opposed to that. But eventually, it all worked out. You got a formal meaning for combining constructs. In the usual model theoretic notions, you have a set of objects, okay? And it didn't turn out too well. This is actually boldface. Not only are there objects like John in the world, but there actually are objects like loves. Loves is not a relationship, it's also an object in the world. It's like there's this, platonic notion of loving or something like that is an object in the world. That's a bit unusual, but there's nothing particularly wrong with it, okay? Names, map, and elements of domain, blank nodes, the usual things, okay? And properties turn into relations, which is a mathematical notion for they relate two things together, two-place relations, okay? And some of the properties have built-in meaning, i.e. there's formal definitions of how they work. They're not just arbitrary things. They have some ideas. For example, subclass, I think that was right here. And namely, this type relationship is the relationship between a class or a category or a set and the instances of that. You have to be careful because they're not really sets that you've learned from naive set theory because they don't obey the principle of foundation. In other words, a set can be an instance of itself in this case. But anyway, it's a reasonable way of describing things. And subclass enforces this subset relationship between a generalization and a specialization, as you would expect. They're essentially blindingly obvious to any mathematical fool. Okay? And domain restrictions, et cetera, et cetera. And we can define inference in terms of this entailment relationship, which is the usual way it's done. Okay? Here's the formal thing that you don't have to understand. Now, okay, so this gives you an idea that now at least you can write a program that does the right thing. Okay? Except, of course, we still haven't told you what John means. All we can tell you is that John means something. Okay, right? And the computer will then manipulate stuff, and as long as John will mean the same thing wherever it sees John, but we have no idea that John means him, right? Or not, as the case may be. Okay, that is not formal properties. That's something outside of our formalism. Okay, and something that we have learned. However, we have learned it. I have no idea. Don't know if anybody else has any idea how we learn the relationship between names in our language and objects or perceptions, or whatever we want to call them in the world, right? I mean, there is this view of the world that there's nothing out there at all. I mean, it's not that it's a figment of my imagination. I don't even have an imagination, right? The world is just, it's not there, right? But we'll assume that it is for the purposes of getting a paycheck at least. Okay, so you still have to have this idea of grounding things in the world, okay? And that's the job of applications or something outside of the formal machine. Okay. So now we're at least in a better situation where at least we have this formal notion of how the semantic web should be built up. Should we build up from this? I mean, not that I've given you exactly the formal stuff there, but I've alluded to it at least. And now we can build new languages on top of that, and we can give them formal meaning the same way that RDF schema is built on top of this. Okay. We can do this for other languages. Okay. And in particular, every language in the semantic web is supposed to be done this way. There's one language to rule over them. Okay? All information in the semantic web is written in RDF XML. All information in the semantic web is carried as these RDF triples. And all these triples carry their meaning as facts. John loves Mary means there's a loves relationship between John and Mary. Whatever John is, whatever Mary is, whatever loves is, there's a relationship between them. Okay. Now, why would we do that? Well, single language means a single parser, right? That's useful, except I can write a bad parser in a day and I can write a good parser in a week. So one might say, so what, right? You can write multiple parsers, who cares, right? There's a little benefit, okay. Another thing is, I can write a tool that extracts meaning from any semantic web document, right? Well, at least part of the meaning. Except, of course, if one of my relationships is not, like negation, so now it's the IR problem, right? What kind of pages do you not want to get when you look for a term to not X, right? Well, some IR does that nowadays, but in general, IR doesn't do that very well, right? Okay, so it does no good if we extract the negation of what's there and claim it's the truth, because we just didn't understand what the negation predicate was. Okay, all right. So this vision, of course, works for RDF because we started in an RDF, right? It works for RDFS because you can do everything in RDF in triples, and you add this extra meaning, et cetera, et cetera, et cetera. And now we get to this OWL language. I haven't said much about OWL yet. But you can actually do this for OWL, and you can force it to work, at least partly. Now the question is, it's like the dancing bear, The question is not how well the bear dances, but whether the bear can dance at all. And so doing this for OWL, have we come up with a dancing bear that we've produced this wonderful artifact that is wonderful only because we actually could do it, as opposed to whether it actually does anything useful. Okay. I'll talk about it later. And unfortunately, this thing breaks down very, very badly when we try to go to more expressive logics, like first-order more expressive languages like first-order logic, and more on this later. Both of these were a surprise, okay? This one turns out was known from 1930s work of Tarski, and I'll try and allude to how it is. Oops, doesn't say here. It turns out that we get the liar's paradox. So in a formal semantic account of reasoning, what is the meaning of I am lying? Is it true or is it false? The answer is you can't give it a meaning unless you break the mold somehow. And this mold is not made to be broken, or maybe it is made to be broken. Okay. So OWL, to start on, OWL is this extension for an ontology, okay? And it allows you to say things like, you know, parents of people are parents, right? We could say every parent is a person, right? But we couldn't say relative things. We could say every parent is an animal, right? For example, parent is a relationship between an animal and other animals, right? But we couldn't then say that the parents of people are people as well as being animals. Woo, not aminals. Okay. You can't even say conjunction, certain kinds of conjunction in RDF. You can't say person with at least one child. You can say person, okay, but you can't make the implicit conjunction in here, okay? You can't make definitions in RDFS. You can't say father is precisely a male person with at least one child, okay? We would like to be able to do that if we're going to describe, well, in this case, familiar relationships, but describe all sorts of relationships between objects and their categories in the world, okay? And OWL does that, okay? So we're building this language that adds ontology capabilities, what we'd like to do. We wanted to fit in the semantic web the same way as RDFS does, i.e., you know, it's written in XML, et cetera, et cetera, et cetera. We would like it to have a well-defined meaning. We'd like it to provide useful capabilities, at least we hope so. And we would like it to be effectively implementable. And therefore, you could build things that actually would build programs that actually would do interesting things for it with it and have them finished before the heat death of the universe. Okay. It turns out that many of these problems are horrendously hard. In the worst case, there's a related language, not OWL, but there's a related language whose worst case complexity is, gee, I've even forgotten the phrase of it, is non-elementary. Okay? Non-elementary function grows faster than Ackermann's. Is that right? Something like that. I forget exactly. But it grows incredibly fast. So heat death of the universe comes very quickly in with this function. But even OWL is non-deterministic exponential time complete. That's a pretty bad complexity class for somebody who was grown up, you know, to believe that, you know, n squared was a bad complexity class. N log n was barely acceptable. Non-deterministic exponential time complete is pretty bad. The moral of the story is it's not as bad as I had imagined. And this seems to be a very common theme these days. Oops, yes, okay. So here's a bit of OWL. This doesn't look very much like XML or even triples. This is actually a syntax for description logics that was chosen by a bunch of logicians who write papers in double column format and therefore want short lines. And so therefore that's why all these logical things. This says something like wine is a particular kind of potable liquid. It has exactly one maker, and every maker is a winery, and it has at least one, it's made from at least one grape, and has exactly one color, et cetera, et cetera, et cetera. So that's what this first thing means, and a bunch of stuff, which I didn't bother to say here. A white wine is a wine that has color white, and Corbin's dry white Riesling is a Riesling that's made by Corbin's, and some other stuff. This is actually extracted from an existing wine ontology. It's been around for quite a while. Okay. So this is the kind of thing that we can say in OWL. We can describe wines and makers and food and various kinds of things and produce definitions about some of them. We can produce complete definitions where we know them, like white wine. And for natural kinds, we can give partial definitions. Or maybe it's not really a natural kind. Maybe we just don't know enough. Maybe there is a complete definition and we don't know enough to get the complete definition. But as far as this thing, wine is a natural kind. It's something that we do not have a complete definition of. We never could recognize something as a wine without being told it was a wine. Whereas a white wine is easy. If it's wine and its color is white, it's a white wine. Again, it's the make form of what should be blindingly obvious. Okay. Now, it turns out, even in this wine ontology, which actually is pretty simple, you feed it in and the system comes up with some inferences and you go, huh? And it turns out that it has made something, it has determined something interesting, and it's hard to figure out exactly why it made some of the inferences it made. Which means explanation is a difficult problem for these things. But anyway, that's not this talk. Okay, now, so here's a syntax for OWL. How many syntaxes for OWL are there? Let me count the ways. 3.5, shall we say. Okay, there's this short one, which I like. Okay, there's a functional style one, which is actually nice to type. Okay, and then there's these. Okay, these all say the same thing, by the way. Okay, this is RDF XML, and I said it was ugly, didn't I? I think I understated the case. And this is essentially the triples that come from this RDF XML. Turns out in this case the triples look perhaps even uglier because to represent conjunctions you have to make lists. And this is how you make lists in RDF triple. This is how you make lists in RDF triple, so it looks a bit uglier than it could be. Essentially this says this L1 is a list whose first element is wine and a second element is this restriction down here, and you're forming the intersection of that list. It's an awful way of doing things, but it's required to fit in the RDF vision of the semantic web. Okay. All right. So, you know, what are we going to do? It's okay. So we believe in this vision of RDF overall, and we have this ugliness. Okay, ugliness isn't so bad. We managed to make it work. We have the syntax, or do we? Well, we've got some things. Okay, we've done all the nice things. Okay, it works. All these things we know for sure. I claim OWL is useful because it encompasses this particular description logic, which actually has shown to be have usages in the past. Okay, and I claim it can be effectively implemented and used, even though reasoning is non-deterministic exponential time complete, because turns out I lied a little bit. For the language I just showed you, inference is actually undecidable, and we'll get into that in a minute. But for a rational cut-down version, it is decidable, okay? And you can restrict it this way, okay? Nevertheless, you can actually build reasoners that work effectively. Now, that doesn't mean that you can feed the entire World Wide Web into an OWL reasoner. It would croak before you fed in the first 100 pages, most likely. Reasonable, I mean a compact set of definitions about a cohesive piece of information and, you know, let's say 100,000 facts in that thing. Then it would work reasonably. By and large. No guarantees, of course, because the worst case is horrendous. Okay, so there's a big caveat to be had there. Okay, so unfortunately, there are these three problems with fitting OWL into the semantic web. We can characterize them as triples, triples, and triples. Okay, why do we say this 3 times? Well, triples are the only syntax. There's 3 facts about triples that cause problems. Triples are the only syntax we're allowed. Triples are always facts. And triples don't distinguish between names. In other words, when you look at things as triples, names of properties, objects, and individuals all look the same. And even worse, names of individuals like John and names of syntactic connectives like conjunction also look the same. Okay. So, solution to this problem took a long time. Okay. So what do we have? The problem is, to put everything into triples, we need to have these list kind of things, which I showed you before. Okay? And this, because this is a fact, we have to have this kind of fact in the domain. Well, what is there about the world that forces there to be a list of this kind? Okay? Nothing, right? Right? It's a list. You know, in computer science, the lists don't always exist in the world. You have to build them, right? Okay. Well, we can fix that by essentially saying by fiat, lists always exist. Okay. This is called the comprehension principle. Okay. And we need it to otherwise OWL won't work out correctly, because when we ask, you know, is a white wine belong to this category? It will say no. Why? Because the syntax doesn't even exist. You can't say it belongs to the syntax because the syntax isn't known to be in the world, and it has to be in the world for it to work out. So here's an example. If John is a person, we can't infer that he's either a person or a rock, because to belong to this, we need a list corresponding to a list, and the list might not be there, okay? Unless we have a comprehension principle that essentially provides the fact that all these lists are floating around. Now, your alarm bells, if you're a philosopher of mathematics, your alarm bells should be going off about now, because then you would say, Russell's paradox, Russell's paradox. What does Russell's paradox say? That essentially, for any predicate, you can form the set of objects that belong to that predicate, and if you say that the predicate says that I'm not a member of me, that there's a set of there's a set whose elements are the things that are not members of it, and the question is it a member of itself. Okay, this is Russell's paradox, or you can do Liar's paradox, or whatever you want. So you have to be very careful, okay? And the solution is to forbid self-reference in the syntax, right? So the Liar's paradox and a lot of these things have this idea that you can have self-reference. The Liar's paradox says, I am not lying, which refers to myself, or this statement is false, or whatever. Russell's paradox has self-reference because you feed the predicate into itself. Okay. So we only allow tree-like syntax, which is reasonable. Non-tree-like syntax, you like it sometimes, but not too much. We haven't cut off too much of our nose to spite our face yet. Okay. But we have introduced all these comprehension principles, and writing them is tricky stuff. Okay. You need to have enough syntax living around in the world so that all your inferences work, but not too much that you have paradoxes. Okay. So this problem was fixed. Okay. Problem 2. RDF doesn't distinguish between classes and objects, or concepts and individuals, or whatever you want to call it. Okay. So classes are in the world. They can belong to themselves, things. And so particularly we can have something like John is a person, okay? And person is itself an instance of this meta class, the class of all classes. Well, okay, that sounds semi-reasonable. It doesn't, it's not too bad. It causes certain problems if you do it the wrong way, because it could be higher order, and higher order logic is very hard to reason with. But this is not really higher order. It just looks higher order-ish. Okay. However, it's not the usual way that we do things in effectively computable logics like description logics. Okay. And it produces certain computational issues, largely because you could say that two classes are the same because of some relationship between the individuals that correspond to them, and that has consequences that could be very far-reaching. So we could say, eagles and porpoises are equal to each other, and that would be a statement about objects, and it would then make all eagles, the class of eagles and the class of porpoises be the same. And you can do that contingently, and it causes reasoning problems. It's still a decidable logic, but nobody has a good algorithm for reasoning in it. Boris Moretic showed this just last year. Okay, so problem 2 we can sort of get around. Okay. Problem 3 talks about the idea that we can have things like conjunction. We can make statements about the conjunction operation. The conjunction. So we can say things that, like intersection is a subproperty of union. So whenever you have an intersection, you also have a union. That sounds very strange. And it turns out it is exceedingly strange. It causes undecidability. And so this is why we have this idea of owl full, okay, which allows this and is undecidable, and owl DL, which I would characterize as a safe and sane version of owl, okay, which forbids all these unusual things, okay, and results in a version of owl that's description logic in disguise. And Ian Horrocks and myself have actually proved that it really is a description logic in disguise, though it doesn't look exactly like one, okay, and it retains just about all the useful parts of owl, and it has effective reasoners with this big caveat. Okay. Certainly not database speeds, but fast enough for interactive usage by and large. Okay. So the thing is, in OWL-DL, we can use this nice syntax, because that's all we get is the nice syntax. So why in the world did we go to this ugly syntax, right? It's verbose, ugly, and confusing. Triples are very verbose as well. The worst of it all is we have all these triples, and we're trying to find out the conjunctions and disjunctions. Turns out that parsing triples into conjunctions and disjunctions and all the other bits of OWL syntax is harder than parsing a decent XML syntax for OWL-DL. Right? So we claimed that we were doing this because we wouldn't have to write parsers, but in the end we have to write a parser that's harder than the usual parsers. Well, that's just annoying in a certain sense, right? Okay. So maybe we could use a nicer syntax, but we haven't really done anything too bad. We've managed to shoehorn OWL into this semantic web vision. Oops. Okay. And then it's just an aside, which I think I'll skip over. Things you can't do in OWL-DL. Okay. But now we want to go beyond OWL. There's things you can't say in OWL. We like to go to full first order logic, okay, fit it into the semantic web, same way we did with OWL. We're going to have to use comprehension principles because we need the syntax to exist, okay. However, first order logic has things like disjunctions and negations, and we have to worry how to do them. And the neat thing about disjunctions and negations is the disjuncts, or the negated part, are not asserted, right? So you have an A or B. It's not you're saying that A is true, you're not saying that B is true, you're saying that one or the other of them is true. But in RDF, if you just made them be triples, they would be true. So what would the disjunction mean? It wouldn't mean anything. You couldn't do it, right? So you have to be very careful here, okay? You need some sort of truth predicate to say which bits of syntax are true. So you have to say that the true thing is A or B. And by the fact you didn't say that A was true, then it's not necessarily true, okay? And you have to encode it. You can't just write it down as a triple. You have to encode it using some pieces of syntax. But the most important thing is you need to have this truth predicate. And now we're sunk. It turns out that in any sufficiently powerful logical formalism, you can have a version of the liar's paradox. And what does it take? It takes a truth predicate and some way of constructing syntax. And that's all. As soon as you have a truth predicate and, you know, conjunction, negation, actually quantification is important too, and some way of constructing the syntax, then you have a version of the liar's paradox. Not this self-referential one, but a diagonalization kind of thing, which is kind of hard to wrap your head around. For any property P, we can say S is true if and only if this property of the encoding of S is true, okay? And then we make PB not true. So S is true even if and only if the encoding of S is not true, okay? And because the encoding of S is not true is true precisely when S is false, this statement cannot be true, but it exists. It's part of our syntax. It exists, and we end up with the paradox. Okay. So we have done. This is the only way we could go. Right. It turns out that the proof of this is very annoying because we don't really have all the machinery we're used to in first order logic. But it comes from an old, very old work from Tarski, and I didn't put the reference. I should have put the reference. We can't escape using some normal ways of escaping because this truth predicate is not something that we've added onto the language. It's defining the first order logic extension. So if we change the truth predicate and make it weaker, which is one of the ways of getting around it, then we have not captured first order logic. So this vision of the semantic web fails if we try and go this high. Right? So what can we do? Is the semantic web a failure? Have we hit the limit of the semantic web with OWL? And the answer is, well, if we come up with the same vision we have, but my claim is that the vision is broken. Okay, we need to change it somehow. So what should remain? Well, the semantic web should be in the web. Okay, yes. Name should be RRIs. That seems reasonable. Should there be some sort of common semantic basis between the semantic web languages? Well, gee, that seems reasonable because if I say something in OWL and you say something in RDF, we'd like them to be able to be semantically compatible somehow. Yes. Now, this is problematic, though. You may think that regular logics work this way, but that's not really quite true. That's only something looking in hindsight that it's true. Okay? And it took a long time to achieve, and there are still some problems in this unified account of all of the sort of regular logics, okay? But it's pretty close to being true, and we can make, some of these problems are fairly philosophical, having to do with whether objects exist forever or whether they can sort of exist at particular times, and if an object starts to exist, can it then cease to exist, right? So we can pick one of those and go with it, okay? There's possible ways of doing that, okay? The minimum semantic requirement I claim for this vision, this modified vision to work, is that when we introduce a new language, we can come up with a new semantic account which relates its meaning to the meanings of the other languages. We may have to change the meanings of the other languages, but as long as that's compatible with their old meaning, we're still okay, because they will still work the same way. The proof of that can be very obnoxious in some cases. Okay. And it may be that if we have like 10 semantic web languages, that some of them are just incompatible. There may be one for time that's that has non-divisible time. So time is infinitely gradated, right? And there may be another one where time goes in uniform time steps. The uniform time steps is much easier to work with. The infinitely gradated one is probably closer to reality, although the physicists have the last word on that, as far as I know. And I don't think they've decided yet. Okay, right. Although, of course, we can guess that their solution will be completely incomprehensible, because it will be, again, you know, there will be all these crazinesses that infect quantum theory will infect a quantum theory of time. Matter of fact, I'm willing to bet money on that. Okay. And so, of course, what part of the vision we don't want is information as triples. I claim there's no real benefit, lots of problems, and no reason. Okay, so to conclude, more or less, okay, my vision of the semantic web then is multiple languages, you know, various things, tautology, rule language, and one for services, by the way. We haven't had anything about how services should fit in here, okay? And by the way, if you've been following this work, I would claim OWL-S is not the way to go. You want a special language, etc., okay? And let a few languages bloom. Hopefully not a few thousand, okay? Oh, bad typo. Oh, well. Languages have compatible semantics and work together. At least you can come up with a reasonable way of doing it. So, for example, the service language talks about, you know, the inputs and outputs of services, and those are described using the ontology language, and the semantic account for that works very nicely. Okay? And that's how you can actually, you can think of then decomposing the inference process. The service language talks about what happens inside the services. The ontology language talks about how you do mappings between the inputs and the outputs of things, and actually how you maybe, to be Googlish, how you can actually find services that actually match the kind of information you're willing to feed it, and services that produce the kind of outputs you're willing to do, and then you actually figure out how it happens inside. Okay, you may have to do some reasoning in that, but maybe just enough to do the input and output matching. Okay, okay, and to allow for different syntaxes when needed. Okay. So, turns out there actually is some machinery in the web, not the semantic web part of the web, but the other part of the web, to make this work, namely MIME types, right? Okay, I am, you know, if I am an OWL processor, I want to look for versions of information that are written in OWL, or RDF if I can hack that. And I can do content negotiation to find the kinds that I really want, if I can accept multiple kinds. And I can import documents, I can point to documents and have references to documents in various ways, okay? And moreover, if I have a name that I don't understand, I can actually look at that name and say, aha, this name probably refers to this particular document. I can then get that document and say, ah, here's information that I probably should believe about this, the referent of this name. Now, I have another harangue about the other part of the semantic web vision, which says you have to believe that document, but that's for another day. Okay, oops, okay. So, that's my vision, and I'm sticking by it. What comes next? How can we make this vision a reality? Well, first there's this ugly thing called politics, right? One has to convince certain web luminaries to buy on to this, right? Because, in particular, the semantic web part of the web is owned by the W3C, and you know, to make it have really uptake, you have to make it be at least, well, blessed by W3C would be best, but at least not incompatible with the vision from the W3C. Okay. Another part, there's no services language yet. Actually, there's a whole bunch of services language around. Let me characterize the situation as I see. The popular ones are no good, and the good ones are not popular. That's a bit prejudicial, but not too far off. Okay, so not LS. Build better tools. There's a lack of tools here. Okay, tools are hard to build. Okay, especially things that are used by users. Right, it's hard to author ontologies. It's hard to author information and do it right. Okay, now. Ideally, one would like to have this happen automatically, but I believe there will be at least a fair bit of human authoring of ontologies and human authoring of information on the web, okay, in the semantic web, okay? But building these tools is very difficult because you're trying to get semi-sophisticated users to write down formal stuff in a way that's compatible with other people's formal stuff. Humans are very bad at this. And getting a tool that works well is very difficult. It's a very tough user interface problem. And I don't have much to say about that because I'm not a user interface guy. Although I'd love to be in a place where we're good user interface people. Anybody out there a good user interface person and willing to admit it? The other thing is, there's lots of data, a lot of it junk out in the web. Sure would be nice if we could build semi-automatic tools for extracting the knowledge out of this. Okay. Oh, sorry, that was a different bullet. Maybe it's not, honey. There's lots of, let me say that right now. There's lots of information on the web. It would be nice to be able to extract some of it semi-automatically. But it would be nice to have a tool that would look around for services on the web and semi-automatically figure out whether it's a service that you can use. I say semi-automatically because if you ever drop out the semi part here and you talk to a business, they'll scream. They'll run away screaming because they don't believe, part of doing business with another business is sending a guy over there to look the guy in the face and see whether he's lying. To put it bluntly. But at least you can do some of the vetting and sort of say, you don't want to send somebody out to this place because they're not doing the right thing. So, lots of work there. Some medium term, some long term, some infinite term maybe. Okay. Oops. All right. And that's the end. Here's a few references of papers that I've done in this area that I haven't mentioned so far. And that's it. Questions? Are we doing questions? Yeah.
So you mentioned the political aspect.
Yeah, ugly politics, right?
Yes. So it seems that that there is some advantage that some parties who are building, we'll say, services, languages, technologies, etc., have a vested interest in keeping parts of their system unintelligible.
One is, there is the business model of places like Amazon.com. We're not in the business of selling services that you can interact with automatically, because it's not the way to do business. Yeah.
Is there any hope for mechanism design so as to make it? This is a human engineering.
Yeah, I think peer pressure is the mechanism that's required. Certainly there are a lot of places that are not multi-megastores, shall we call them, that would be very happy to do this kind of thing, because they're interested in selling you what you want, as opposed to something else. And that's the whole user interface of Amazon. Sorry to pick on Amazon.com, but as I've said multiple times, the whole user interface of Amazon.com is designed to sell you another book. Or another something, books initially.
How does this effort relate to something like Psych?
So, those of you, Psych is this attempt to build
A big database that has all these relationships between
a theory of everything, right? Right. So Psych, if you remember the theory, what's the trilogy? Hitchhiker's Guide to the Galaxy, right? Psych is the attempt to do what the people who built Earth did, right? Find the answer to everything. But they did it a different way. So Psych's idea was to build up in a particular logic, right? Lots of information, lots of common sense information, right? I'm not saying there will be any common sense information here except incidentally, right? I don't care to know a theory of liquids, okay? I care to know a theory of familial relationships because people write down familial relationships on the web, and therefore there should be a theory of them. I care to know a theory of different kinds of books because booksellers sell different kinds of books on the web. Okay? So again, the goals are different. I'm much more also willing to have disparate information. I'm not saying, it's like the web and the semantic web, I'm not saying that all the sources of information on the semantic web will be mutually coherent, that they won't, right? Okay? And Psych's initial goal was everything should be mutually coherent. Now, they changed that because they realized they couldn't do it. That's why they have this idea of microtheories. But in some sense, this is, at some point, something similar to microtheories idea.
And does Psych's effort to represent their common sense logic have any tending to feed into this problem?
Yes, in a certain sense. The trouble with Psych is that a lot of its representation is intimately tied with its inference engine, which is, to put it bluntly, peculiar. Okay? But it's peculiar because it's an engineering artifact. Okay? And if you're so engineering is the process of making possible by tricks what would not be possible without the tricks. Right? And the trouble is, if you're building a big artifact, you have to be very careful with how many tricks you put in, because eventually the bridge falls down. Right? And that's the trouble with the Psych inference engine, is there's so many tricks in there designed to get particular things to work, because they had demos or customers that they had to get their inference engine to work. And the trick was put in to make it work better there, which is good, okay? But if you're not careful, you do it in a way that's not pure, and that impurity starts to infect other things. Okay? That either might have had to because they would be too slow, but even worse, but it would have worked normally without this trick, but with the trick it works a little bit faster, and so you're tempted to use